We will start the new class, Module 4. In the previous class, we discussed about the metals. Now in this class, we will discuss about non-metals. I am Manjunath I, Assistant Professor, BITM, Ballari, Mechanical Engineering Department. Let's start with content. What we will discuss in this class. We will discuss polymers, ceramics, smart materials. First, we will discuss about polymers. Polymer chemistry. Any class of natural or synthetic substance composed of very large molecules called macromolecules that are multiples of similar chemical units called monomers. Polymers make up many of the materials in the living organisms, including, for example, protein, cellulose, and nucleic acid. As we say, polymers are generally a giant chain of macromolecules. Polymers can be synthetic or natural. Generally, we will discuss about the polymers that are synthetic, man-made polymers. What are thermoplastics? Thermoplastics are organic material which will melt when heated. Before we go to the when heated, they should be differentiated from thermoset material, which cure or become set when they are heated. Thermoplastic material are melt processable, that is, they are formed when they are melted or viscous phase. This generally means they are heated, formed, and then cooled in their final shape. Generally, thermoplastics or material are linear in structure. Since they are linear in structure, they can be melted. Polymers generally thermoplastic will usually have a melting range. Unlike metals, which will have a melting point, say example, steel will melt at 15-30 degrees Celsius. At the exact point of 15-30 degrees Celsius, steel will melt. Not for polymers. Polymer will have a range. Take example, high density polyethylene, which will have a melting range of temperature 90 to 120 degrees Celsius. So these are thermoplastics. Thermoplastics. Thermoplastics have a simple molecular structure comprising chemically independent macromolecules. Upon heating, they are softened or melted. Then they are shaped, formed, welded, and solidified when cooled. Cycles of heating and cooling can be repeated, allowing the processing and recycling. Generally, thermoplastics can be reprocessed, means can be melted, or can be recycled. Because they got a linear structure. Application of thermoplastic means we have ABS thermoplastic is there, which is used for sport equipment, toys, various automobile components. Usually the automobile bumper, the front bumper, the back bumper, they are made up of ABS. Even fuel tank is also made up of ABS. Whenever you see an automobile, the fuel tank is made up of plastic. ABS is used. Polycarbonate is an engineering material. CDs, DVDs. Nowadays we don't see much of CDs or DVDs. Drinking bottles, food storage containers, eyeglasses, lenses. Polyethylene is the most commonly used thermoplastics. Shampoo bottles, plastic, grocery bags, bulletproof vest. Ultra high density polyethylene. Polyethylene is a family in which we have high density polyethylene, low density polyethylene, linear low density polyethylene, ultra density polyethylene is there. So ultra molecular density polyethylene is can be used for bulletproof vest. Thermosettings. Till now we discussed about thermoplastics. Now we will discuss about thermosetting. Thermosetting is a polymer that are irreversible, becomes rigid when heated. Such a material is known as thermoset. A thermosetting polymer, initially the polymer is in liquid or soft solid. Heat provides energy for chemical reaction that increases the cross-linking between polymer chains, curing the plastic. The rate of curing may be increases in many cases in increasing the pressure or adding catalyst. Usually thermoset plastics forms a 3D structure. Curing takes place once the curing is over. They are 3D structures. Example for thermosets are many plastics are thermoset. They are include vulcanized rubber, fiberglass, polyester resin, epoxy, silicone resins. These are the few examples of thermoset application. The thermoset applications include the construction equipment, panels, electrical housing, components, insulator, cell tops, shield, circuit breakers, agriculture feeding, toughness, motor components, disc, brake, pistons. The difference between thermoset and thermoplastic. Here the pros and cons of thermoset, both thermoset. More resistance against heat, high temperature. The cons is cannot be recycled. Hard and rigid, much more difficult to surface finish. Excellent finish, cannot be molded or reshaped. High mechanical property, poor thermal conductivity. Cost effective, rigidity of the material, or may not be used for damping properties. Means poor damping properties. Excellent dimensional stability. Ceramics. Till now we discussed about polymers. Generally the conclusion of polymer is a polymer is a giant chain of macromolecules. Polymers are abundantly available. There are two kinds of polymers generally we have. One, we have an engineering polymers which will have engineering properties. Then we have commodity polymers are there. Generally they don't have engineering properties. So till now we discuss about the engineering polymers. Polymers are most commonly used in day-to-day life. Whenever you see a toothbrush, your clothes, the cloth is not completely made up of pure cotton. Some amount of polymer is involved. Some amount of plastic is involved, you can say. It can be a natural polymer or synthetic polymer. Generally nowadays we use synthetic polymer. And we also discuss about thermosets and thermoplastics. Thermoplastics can be melted, recycled, can be melted again and again. Nothing will happen. It's a simple linear structure is there. Generally like that. A thermoset, once they are set, cannot be remelted or cannot be reused. If you supply the heat, try to melt the material, then the material will simply degrade. That means it forms a 3D structure. Once they are set, they are set. Recycling of this material is difficult. Remelting cannot be done. The material will simply degrade. The application of polymers are various polymers, thermosets and thermoplastic we also discussed. Now we will discuss about ceramics. Ceramics are inorganic materials. Polymers are organic materials. Ceramic is an inorganic, non-metallic solid made either of metal or non-metal components that are shaped and hardened by heating to high temperature. Generally, they are hard, corrosion resistant, and brittle. Generally, ceramics are inorganic materials, and polymers are organic material. What is organic means? Anything the backbone is carbon is an organic, other than carbon is an inorganic. Advantages of ceramic means high wear, high pressure. They can withstand high wear. They can withstand high pressure, high heat, and chemical attack. Chemical attack, extreme environment. That's the reason why glass is used to keep the pickles, to keep the salt. It can withstand very corrosive environment compared to a metal. Extremely hard, extreme hardness, excellent electrical insulation, light in weight. Compared to metals, you can say the ceramics are light in weight. We are comparing ceramics with metals, not with ceramics with polymers. Generally, polymers also light in weight, ceramics also light in weight. Disadvantage of ceramics means extremely brittle. One of the difficulties of ceramic material means they are extremely brittle. Take an example, you take a glass and you drop it. The glass will be shattered into pieces. Glass is nothing but a ceramic material. Weak in tension, obviously. Good in compression. Poor shock resistance, means poor impact load. Can crack when hit with heavy items. Application means they are used in space industry. They are used for cutting tools, refractory material, thermal insulator, electrical insulator. Insulator. Insulator is the material that does not conduct electrical current. Insulating material include paper, plastic, rubber, glass, and air. Vacuum is also an insulator, but it is not actually a material. Most electrical conductors are covered by insulation. The last topic that we'll discuss in this class will be smart materials. What are smart materials? In the class 1 we discussed about the Stone Age, the Bronze Age, the Iron Age. We discussed more in detail about the Iron Age, the steel, and the ferrous material and non-ferrous material. If anybody asks a question, what age we are, we can say that we are in an artificial intelligence age. When you think of material, what age the materials are, we are in a smart material, in the age of smart materials. The most important thing to remember is there is no engineering without materials. There cannot be any advancement of robots or any part of the engineering without materials. You take battery, we have reached the capacity, the battery capacity, the solar panels, wherever you look at it. The limitations what we are encountering is with the material, even with robotics. So the advancement of material is the first, or you can say it is the key to unlock the potential of the future engineering technology. You cannot unlock the future engineering technology without unlocking the materials. Smart material is the key to unlock all the future technologies, whether it is biomedical technology, whether it is computer science, whether it is robotics, whether it is mechanical, any part of the engineering you take it, there is no advancement without the advancement of materials. The smart materials. What are smart materials? Smart materials, take example, our skin. Our skin has a feedback. If something sits on our skin, take example a fly or a mosquito. Take example mosquito. If you now recently we discussing about coronavirus. Coronavirus has killed so many people. Who is the greatest predator that killed more number of people than any other thing in the world? You think of lion, you think of cheetah, anything. It is mosquito. Mosquito has killed more people than any other predator in the world. Take example, if a mosquito, we understand, our mind understands that mosquito is quite dangerous. If a mosquito sits on our hand, our skin will give the feedback to the brain that mosquito is sitting on our hand. Then what we try to do is we try to remove the mosquito from our hand by using another hand. The signal comes from the mind itself. I take example in any part of the body where a mosquito is sitting and sucking the blood. The skin will give the instant feedback to the mind that here the mosquito is sitting, you need to take an action, your hand will come to get rid of the mosquito. That's a smart material. Your skin is a smart material. Our skin is a smart material. So it's a smart material. It's a naturally occurring smart material produced by nature or God, whatever the name you can say it. It is produced. We want to replicate the same qualities in a material so that the material can also feel when there is an external stimulus is given. So smart materials are also called as intelligent material. Our skin is intelligent, right? Or responsive material. Our skin do respond. They are designed material that have one or more properties that can be significantly changed in a controlled fashion by external stimulus such as stress, moisture, electric or magnetic field, light, temperature, pH or chemical compounds. Generally it says that whenever you supply an external stimulus, it can be stress, it can be heat, it can be any of the things, the material will respond. Those are known as smart material. One of the examples for a smart material is piezoelectric material. You can see this is a diagram of a piezoelectric material. This is another diagram, piezoelectric disc generator, a voltage when deformed. Change in shape is greatly exaggerated. You can see original shape is there. When you apply the compressive stress, the output voltage same polarity as material. Whenever you supply tensile force, the output voltage opposite polarity as material. This is expansion and contraction. Whenever the expansion of the material takes place, same polarity. Contraction happens, opposite polarity. These are the diagrams you can see. Piezoelectric. Piezoelectric is the ability of certain materials, piezoelectric material, to produce a voltage when they are subjected to mechanical stress. Basically, they generate electricity whenever stress is induced. Piezoelectric material also show the opposite effect where the application of electric field creates mechanical stress. Size modification in the crystal. Internal working. The effect of explained by the displacement of ions in crystals that have non-symmetrical units. When the crystal is compressed, the ion in each unit cell are displaced, causing the electric polarization of the unit cell. Because of regularity of crystalline structure, the effect accumulates, causing the appearance of the electric potential difference between the certain forces of the crystal. When an external electric field is applied to the crystal, the ions in each unit cell are displaced by electrostatic force, resulting in the mechanical deformation of the whole crystal. This is the internal working. The application of the piezoelectric material, the mechanical to electrical conversion, phonographic cartridges, microphones, vibration sensors, accelerometers, photo flash actuators, gas igniters, fuses. That is from mechanical to electrical. Suppose we use electrical to get into mechanical, we got valves, we got micro pumps, we got earphones and speakers, ultrasonic cleaners, emulsifiers, sonic transducer. The advantages is high strength, good electricity, fatigue resistance, wear resistance, fabrication, light in weight, shape memory. A shape memory alloy, or you can say a smart metal memory alloy, are alloys that can be deformed at one temperature but when heated or cooled return to their original shape. The alloy appears to have a memory. These are the few materials that are given: nickel, titanium. SMA exhibits super elasticity behavior. Basic working principle is SMA has two stable phases: high temperature austenite, low temperature martensite. Martensite has two forms, twinned and detwinned. The phase transformation which occurs between these two phases upon heating or cooling is the basis of which unique properties of SMA. Austenite, high temperature phase, cubic crystal structure. Martensite, low temperature phase, monoclinic crystal structure. Twinned martensite, detwinned martensite. Martensite means a needle-like structure. If you see in an electron microscopy, the shape is like a needle. These are the diagrams that are shown: austenite, cooling, detwinning martensite. When the load is applied, deform the material. When the heating is done, then it comes back to its original shape. Heating and cooling. Upon cooling, in the absence of applied load, the material transfers to austenite into detwined material. Upon heating, the material in the martensite phase reverses the phase transformation take place as a result of material transfer to austenite. If the mechanical load is applied to the material in the state of detwinned martensite at low temperature, it is possible to detwin the martensite. You can see in this diagram how it is done. Martensite, deforming under martensite, austenite. When temperature is produced, then under martensite condition. These are the application. You can see bone plants, surgical filters, eyeglasses. You can see B-2 bomber, US Air Force B-2 bomber. It's a fly-by-wire technology which uses a supercomputer. Since it does not have any tail, you can see it. Look at this B-2 bomber. It does not have any tail. Generally, planes do have a tail. If the planes do not have a tail, then the stability of an aeroplane, controlling the aeroplane in the air, is, if not impossible, it is difficult. Then how it is controlled in this bomber is they use a supercomputer and they use the nitinol as the smart material for fly-by-wire technology they are using. So this stability cannot be found in an ordinary airplane if nitinol smart material is not used. So that's the reason why all the planes have tail. Why tail is removed and why we go for such complicated design is to remain invisible to radar. You don't want any kind of a thing that obstructs and can be visible on a radar. If a tail is there, it can be visible. What are the advantages? Means biocompatibility, diverse field of application, good mechanical properties. Disadvantages: expensive, poor fatigue properties, over stress. So this will complete the non-metals part of the class 2 chapter 1 engineering materials. In the next class, we will discuss about the last remaining topic, the composite material. If you have any kind of doubts about the non-metals, you can able to ask those questions directly to us using Google Classroom. And how do you summarize this? Summarize this part is these are finally the summary. These are non-metals. Non-metals come into the popularity or high in demand due to various reasons. One of the reasons why non-metals are become such a popular is they are corrosion free. Why do the toothpaste brush or a toothpaste or a bottle, wherever you see, they are made up of plastic? Why do the ceramic glass is used? Because they are corrosion free. They don't resist corrosion. No matter how many years you keep it under they are corrosion free. Whereas metals, generally non-ferrous materials, they are corrosion resistant. They can resist the corrosion for a very long time, but eventually they will corrode also, like ferrous material. Whereas non-ferrous material, no matter how much you have, they are corrosion free. That means they will never corrode under any circumstances. That's the reason why they are popular. Other reason why the popularity of polymers is high, because of low processing temperature. Hardly 120, 150 or 160 degrees Celsius is required. When you want to store the water, want to brush teeth, generally we are working under room temperature. At that kind of a temperature, they can be very easily used. It's not a problem. Only the problem with non-metals will come when we are using under a generally polymers under high temperature. We will discuss what are the difficulties that we face in non-metals and how they are overcome in composite material in the next class. Finally, smart material. Smart material is a new age material. I'm going to say this current generation of material, 21st century. It started with smart material. These are the materials which will have a tremendous promise for the future of the mankind. These are the material which will drive the next industrial revolution, the fourth industrial revolution. These materials will be, you can able to see them very widely used everywhere in the world. Just we briefly introduce a smart material. These are the material which will change to the external stimulus that is given. The external stimulus can be stress, temperature, electricity, any kind of external stimulus. If it is provided, the material will respond. We call them as intelligent material, smart material. There are various materials are there, like self-healing material which can heal itself very rapidly. Nowadays we use the self-healing material in International Space Station. There are a lot of space debris is there. In space, lot of particles or dust, some moving at very high speed. If they hit the space station, what will happen is it will puncture the space station. Whatever the air is there will be sucked out into the space, and the people, the space station will become unviable. So we use a self-healing material. Whenever there is a puncture of hole happens in a space station, it will instantaneously heal that spot to make sure that the air does not leave the space station into the space, like that. There are various other kind of smart materials. We have self-healing material, we have magneto-restrictive materials, we have piezoelectric material, we have a shape memory alloy material is there. You got shape memory. Polymer is also there. There are various materials we are currently under development. The future looks quite bright for the smart material. So here in this one we will end the this class about the non-metals. Thank you.